It's common to picture the night sky as a cold, empty vacuum, a dark expanse dotted with the occasional burning star or dead, rocky moon. But that picture is incomplete. Deep space is actually a factory of extreme chemistry. When you introduce immense gravitational pressure and adjust the scale, matter behaves in completely unexpected ways. Take, for example, a solar system where the chemistry is heavily skewed. If a planet forms with significantly more carbon than oxygen, the standard rules of rock and gas disappear. Inside such a world, immense gravitational pressure forces loose carbon atoms together, crushing them into a rigid crystalline lattice. The planet effectively becomes a gigantic diamond. Astronomers found one candidate orbiting a pulsar, the rapidly spinning remnant of a dead star. At these scales, gravitational pressure acts as a builder, forcing matter into the precise, unyielding geometries of a crystalline world. While these carbon worlds are locked in rigid crystal, living stars are fluid, churning spheres of superheated plasma. Inside these stars, deep, slow pressure waves travel through the gases. The star actually pulses and vibrates, a phenomenon studied in a field called astroseismology. Astroseismology is the study of stellar quakes, measuring how internal sound waves cause the surface of a star to oscillate. Scientists listen to these silent, rhythmic pulses by tracking tiny changes in a star's brightness. It acts like cosmic echolocation, allowing us to map the hidden structures and flows of hot gas deep beneath the surface. But this delicate balance of internal pressure and outward energy has a limit. Some stars grow so massive that their own gravity becomes an inescapable weight. When they run out of fuel, these super heavy stars don't explode. Their cores collapse so suddenly that the outer layers fall straight in. In a fraction of a second, the star vanishes, leaving only a black hole. The internal architecture of these celestial bodies dictates their fate, whether they sing their continuous seismic songs across the void or succumb to gravity and slip quietly into darkness. When we zoom out from isolated stars, we find that gravity forces massive objects to interact with one another in complex orbital dances. In some systems, known as contact binaries, two stars orbit each other so tightly that their outer atmospheres physically brush against one another. This fluid simulation captures the mechanics of that exchange. As one star swells and ages, its outer layers spill over, creating a delicate, spiraling river of superheated plasma that is siphoned directly onto its companion. That intimate physical connection sits in contrast to the vast distances currently separating stars in our own celestial neighborhood. Yet some astronomers believe our solitary sun was actually born alongside a twin. Over 4 billion years ago, a companion star likely formed from the exact same cloud of gas and dust. Over eons, the slow, relentless gravitational tug of the Milky Way disrupted their shared orbit. The lost sibling was pulled away, left to drift on an entirely different path through the galaxy. The paths these stars follow today remain shaped by the physical and gravitational connections of their past. Pulling back to the largest scales reveals that these orbits and trajectories aren't playing out on a flat, static canvas. This diagram illustrates general relativity. The shape of space is actively warped by the mass of galaxies within it. Because of this curvature, traveling in a straight line could theoretically lead you back to your starting point. Holding this curved geometry together is an invisible scaffolding known as the cosmic web. The cosmic web is the large-scale structure of the universe, consisting of enormous formations of dark matter and gas separated by giant voids. Dark matter gathers along these filaments, connecting vast clusters of galaxies across billions of light years. When mapped out, this interconnected structure resembles a massive neural network inside a human brain. Across billions of light years, this interconnected web defines the macroscopic architecture of the cosmos, grouping galaxies into a single structured entity. We can trace the gravitational pull of these cosmic filaments all the way down to our immediate galactic neighborhood. This image shows the Andromeda Galaxy, our closest massive neighbor. It contains roughly 1 trillion stars and sits 2.5 million light-years away. Driven by the geometry of our local gravitational web, Andromeda and our Milky Way are currently locked on a slow-motion, unavoidable collision course. In about 4 billion years, the main bodies of these galaxies will begin to merge. But the vast, invisible outer halos of hot gas and dark matter surrounding both of them are so expansive that they have already begun overlapping. In a physical sense, the two galaxies are already touching. From the extreme microscopic pressure of a diamond core to the slow-motion embrace of colliding galaxies, we are embedded in an elegant, deeply interconnected geometric masterpiece. The Big Bang was a gentle, massive expansion of space itself. It began as a bloom of heat, blooming into a vacuum that did not yet have a name. Measurements of the cosmic microwave background place the age of this expansion at roughly 13.8 billion years. The cosmic microwave background is the residual thermal radiation left over from the early universe, now stretched into cool microwaves. However, recent observations of ancient stars are creating a scientific contradiction. These stars appear older than the 13.8 billion year limit, suggesting our current calculations of the universe's age are incomplete. This tension supports the cyclic universe theory. This model proposes that what we perceive as the beginning was actually a bounce from a previous iteration of space. This diagram shows that infinite rhythm. The universe expands to a maximum point, collapsing inward under its own mass before rebounding into a new expansion. While this collapse resets the physical structures, it carries forward subtle ripples from the universe before it. Time itself is an endless, rhythmic loop. It stretches across spans of time so large they dwarf our individual lives, turning the story of the universe into one of constant, rhythmic renewal. If we move away from the light of the early universe and look into the darkness between star systems, we find absolute isolation. This darkness is home to rogue planets. Rogue planets are worlds that have no host star and instead drift alone through the galaxy. These worlds are born in two ways. Some are formed normally and then ejected from their systems by gravitational chaos, while others form in isolation as failed dark stars. Billions of these wanderers drift through the Milky Way. They are so common they likely outnumber the actual stars in our sky. On their surfaces, the environment is frozen and silent. There are no sunrises to mark the passage of time, only the faint glow of distant, unreachable stars. This silence is a stable, permanent feature of the cosmos. Absolute solitude is the standard experience for a significant portion of the matter in our galaxy. Beyond the scale of single planets, entire galaxies are bound together by gravity. The Milky Way is on a path towards its nearest large neighbor, moving through the void for a rendezvous that will take billions of years to complete. That neighbor is the Andromeda Galaxy. It is a massive, glowing spiral containing 1 trillion stars, closing the gap between us at a steady pace. This interaction is a gravitational blending. Gravity will pull the two systems into a mutual orbit, slowly weaving their structures together over eons. As shown, stars are so distant they pass through each other without colliding. The merger is truly driven by gas and invisible dark matter, which comprises most galactic mass. Its gravity pulls stars into long arcs, settling them into a new shape. These massive events are transitions of quiet, immense scale. The universe consumes its old structures to forge something new, turning two spirals into a single, massive elliptical galaxy. Once the blending is complete, the resulting galaxy will spin in the darkness as a single, stable entity. We see this same stability at every scale, from a universe that breathes through cycles of time to a lonely planet finding its path in the dark. The cosmos is defined by this graceful, ceaseless drift. Even its most massive changes occur with a rhythmic patience that prevents chaos. Because we are made of stardust, we are a part of this same slow-motion evolution. We are the universe momentarily observing the mechanics of its own quiet progress. Understanding this scale brings a sense of stillness. We exist within a system that recycles its light and maintains its rhythm, moving with a permanence that will continue long after the stars we see tonight have faded. For the first 380,000 years after the Big Bang, the universe was completely opaque. It was filled with a hot, dense fog of plasma, an ionized gas where electrons and nuclei move freely. That was so tightly packed, light couldn't travel a fraction of a millimeter without scattering off a particle. As space expanded, the temperature eventually dropped enough for those scattered electrons and nuclei to bind together and form the first true atoms. The moment that happened, the fog vanished, and light was suddenly free to travel across the cosmos unhindered. This animated diagram illustrates how those original waves of light have behaved over the last 13 billion years. As the fabric of space itself expands, it physically stretches that ancient light, lengthening it into the cool microwave frequencies that we call the cosmic microwave background. The faint glow of those microwaves is everywhere around us right now. The oldest signal we can observe in the night sky precedes every star and galaxy. It is the physical memory of the moment the universe became transparent. Hundreds of millions of years after that first light broke free, gravity pulled vast clouds of pure hydrogen and helium together to forge population 3 stars. These were the very first stars to ignite, born into a cosmos entirely devoid of heavier materials. Because they contained 0 metals, they grew to enormous proportions, burning hundreds of times heavier and 1,000,000 times brighter than our own sun. That sheer size meant they burned through their fuel rapidly, collapsing in spectacular supernova explosions after just a few million years. Inside the intense heat and pressure of these short-lived explosions, the first heavy elements were forged. When these massive stars detonated, they seeded the surrounding gas clouds with the raw materials needed to build rocky planets, to form giant asteroids, and eventually human beings. These early giants initiated the luminous universe we study today. Yet the combined mass of every glowing star, gas cloud, and dust grain fails to account for the gravity required to hold the cosmos together. We can watch the mechanics of visible gravity play out in binary star systems. When 2 stars orbit close to one another, their gravitational pull can cause them to swell and gracefully spell outer layers of plasma back and forth in a delicate, spiraling exchange. This fluid choreography scales all the way up to entire galaxies. When massive clusters of stars collide, they rarely crash into each other directly. Instead, they slowly slide through one another over billions of years, drawing out long tidal tails of stars and gas as they merge. This chart compares the slow rotation expected from a galaxy's visible mass with the dangerously fast speeds actually observed. If only glowing matter held them, they would rip apart. To correct the math, the model adds a massive, invisible dark matter halo enveloping the system. The swirling arms of gas and light we capture through our telescopes represent only the bright centers of much larger structures. The elegant cosmic dances we observe are actually being guided by an unseen, overarching entity. If we look deep into the isolated voids of space, we find the clearest evidence of this hidden architecture. Astronomers have discovered ghost galaxies, massive collections of cosmic material that contain virtually no stars at all. These systems are brimming with gas and enormous gravitational pull, yet they show almost 0 evidence of star formation. They drift silently through the dark, never gathering the necessary friction or density to ignite into blazing light. These ghostly systems are composed almost entirely of dark matter. Dark matter is a form of mass that refuses to interact with the electromagnetic spectrum. It cannot absorb, reflect, or emit light in any way, but it still exerts a profound gravitational grip on everything around it. Without the blinding glare of billions of stars to distract us, these dim systems reveal the true structural foundation of our cosmos. The architecture of the universe is built from these silent, invisible skeletons holding everything else in place. That same invisible scaffolding permeates our own cosmic neighborhood. Our own solar system is currently drifting through the middle of the Milky Way's massive dark matter halo. As Earth orbits the Sun, we are constantly sweeping through this field. Right now, trillions of dark matter particles are passing through every single square centimeter of your body every second. We never feel this relentless volume because dark matter is completely indifferent to normal matter. These particles ghost right past your atoms without colliding, interacting, or leaving a single physical trace. The immense gravitational glue required to hold distant galaxies together exists as a quiet, continuous stream of mass flowing intimately through the room you are in. This essential force passes through us constantly, even as we sleep. The moon feels like a permanent fixture in our night sky. However, it is drifting away from us, spiraling outward into the dark void. Every year, the moon moves about 3.5 centimeters further from Earth. This is the same rate at which your fingernails grow. This separation happens because of tidal friction. As the moon's gravity pulls on Earth's oceans and the Earth spins beneath them, energy is transferred. This transfer pushes the moon's orbit outward. It is a quiet, relentless retreat. We rely on gravity to keep our world safely tethered together, but out in the dark, gravity behaves in ways we might not expect. Because the moon is slipping away, we must look closer at the force governing its path. In the early 20th century, Albert Einstein realized gravity functions as a physical distortion, replacing the classical concept of an invisible rope or a magnetic tether between objects. Understanding how the cosmos moves requires us to set aside the idea of an invisible rope. We have to visualize the universe through a completely different, tangible framework. Envision the universe as a vast, stretchy fabric, pulled taut like a cosmic trampoline. Place a heavy weight, like Earth, onto it, and its mass creates a physical dip in space. The moon follows these slopes, rolling along the curved indentation. Gravity is the geometry of space, reacting to the physical weight of matter. If we swap the Earth for a supermassive black hole, the physics become extreme. The immense mass of a black hole presses down so fiercely that it plunges the fabric into a steep, nearly bottomless funnel. This fabric weaves space and time into a single tapestry called spacetime. Because they are the same material, gravitational warping physically stretches the threads of time. This is gravitational time dilation. Time passes much more slowly near a black hole. Gravity, space, and time function as a single unit, bound together in an interacting dance. This fabric model is elegant, yet cosmic data contains whispers of broken rules. This is the cosmic microwave background, the residual heat map and earliest picture of the universe. On the right side, there is an unusually large dark blue patch called the cosmic cold spot. It is significantly colder and emptier than physics dictates. This massive void remains an unsettling puzzle. It demonstrates that the fabric of our universe holds flaws that current math cannot explain. While cosmic voids show us the isolation of deep space, gravity also pulls phenomena together with fierce intensity. In binary star systems, two liquid-like stars can orbit each other so closely that their outer layers physically touch. As their gravity wells overlap on the fabric of spacetime, they begin a spiraling exchange. One star swells and spills its plasma onto its partner. The same extreme gravity that isolates black holes can also force objects into a graceful, fiery merger. Gravity acts as the ultimate sculptor. It pushes moons into the dark, slows time to a crawl, and pulls stars into close embraces. These movements are the result of heavy weights resting upon a stretchy, melancholy fabric of reality. The universe is a ceaseless, graceful choreography, playing out through slow ripples across the dark fabric of spacetime. On a clear night, the sky appears peaceful and stagnant. It looks like a simple, empty void, decorated by thousands of distant points of light. But the vast majority of our reality is hidden from view. Everything we can see, every glowing star and every visible galaxy, represents less than 5% of the total universe. If you could peel back the darkness, you would find an active, grinding mechanism. Beneath the starlight lies a rigid architecture of invisible forces that engineers the movement of everything we know. To understand the universe, we have to look past the glowing lights and map the interconnected clockwork of gravity, space, and time. Space itself is not an empty container. It behaves like a physical, bendable fluid, a fabric that reacts to the massive objects placed within it. Massive objects work this fabric. A supermassive black hole bends space so severely that it traps light and pulls the surrounding geometry inward. In these extreme regions, a black hole functions as a funnel of time. The rules of standard geometry break down, leaving only a one-way path toward a single, dense center. We see this same mechanical distortion on an even larger scale when we look at galaxy clusters, groups of thousands of galaxies held together by immense gravitational weight. This concentration of mass triggers gravitational time dilation. Time dilation is a physical phenomenon where time passes more slowly in regions of strong gravity compared to the empty spaces between galaxies. Gravity functions as the primary gear of the cosmic machine, actively stretching the passage of time as it binds matter together. We can see this engineering at work in our own neighborhood by looking at the casing of our specific machine, the Milky Way. Our galaxy is more than just the glowing spiralons we see in telescopes. It is encased within a vast, invisible structure known as the hidden halo. This halo is an immense sphere of dark matter and diffuse gas. It extends hundreds of thousands of light years beyond the furthest visible stars. This unseen mass provides the gravitational force necessary to stabilize the entire system. Without this invisible scaffolding acting as the machine's casing, the Milky Way would lose its grip on its outer stars and tear itself apart. To see this scaffolding in the early universe, we use the James Webb Space Telescope. It is a literal time machine designed to capture light from the deep past. Light travels at a constant speed, but the universe is so vast that signals from distant objects take billions of years to reach us. Looking further into space allows us to see galaxies as they existed in the distant history of the cosmos. This diagram illustrates how the expansion of the universe stretches that ancient light on its journey toward us. As the space between galaxies grows, the light waves are pulled into longer, redder wavelengths. Capturing these reddened signals proves that the mechanical expansion of the universe has been a continuous process since the beginning of time. When we zoom out beyond individual stars and ancient galaxies, we can finally view the universe on its most absolute scale. This is the cosmic web, the overarching blueprint of reality. The cosmic web is a vast, interconnected network of dark matter and gas that dictates the position of every galaxy in existence. Galaxies cluster along thread-like filaments, forming a complex lattice separated by massive, empty cosmic voids that span hundreds of millions of light years. This macrostructure shares a precise structural logic with the microscopic networks inside the human head. The dense nodes of galaxies mimic the behavior of neurons, while the dark matter filaments act as axons, connecting the system into a singular, functional web. This mimicry reveals a universe that is a singular, interconnected machine. Because we are built from the same atoms found in these filaments, our ability to map the cosmic web is simply a microscopic part of the machine observing its own design. When we look up at the night sky, we picture a vacuum, a silent, still void where nothing moves unless it is thrown. But that absolute stillness is an illusion. The cosmos actually vibrates with unseen energy, and we do not have to look any further than our own sun to hear it. This diagram shows the internal structure of a star like our sun. Deep inside, intense pressure waves ripple through the hot plasma, bouncing from one layer to another. This sets the entire star into a continuous vibration, causing its surface to heave and ring like a massive bell. Scientists study these internal waves through helioseismology, which is the measurement of how solar pressure waves affect the sun's physical surface. And as this data visualization traces their light curves, we see how astronomers expand this approach to astroseismology, the study of stellar oscillations in distant stars. They measure rhythmic changes in surface brightness to effectively listen to the hidden internal structures of stars lying millions of light years away. The empty spaces between worlds are active. The universe is a living symphony of vibrating plasma, and decoding those deep rhythms allows us to map the anatomy of the cosmos. That rhythm stretches back to the dawn of the universe. In the outer fringes of our galaxy, we find ancient celestial bodies over 13 billion years old. These stars carry the chemical signatures of the early cosmos, formed when there were almost no heavy elements to build with. This graphic shows how the light emitted by early stars acts as a traveling memory. As it travels over billions of years, expanding space physically pulls the waves along, stretching them into longer, cooler infrared intervals. As stars age, their internal rhythms physically change. Some dying variable stars begin to pulsate. Their outer layers of gas expand and cool, then collapse and heat up again, creating a rhythmic cycle that mimics a slow heartbeat. For smaller stars like our Sun, that heartbeat eventually stops. They slowly shed their outer layers of gas entirely, leaving behind a white dwarf. A white dwarf is a dense, intensely hot stellar core that no longer produces new nuclear energy. From there, the tempo slows to a crawl. The remaining core takes billions of years to gently radiate away its leftover heat, slowly dimming until it fades into total darkness. The universe records its history through these fading rhythms. Stellar death is rarely a sudden vanishing act. It is a measurable countdown playing out over cosmic epochs. But there are disruptions to that steady rhythm. Some of the most massive stars skip the brilliant supernova explosions entirely. They simply blink out of existence, leaving nothing but an empty void. This happens through a process known as a direct collapse. A direct collapse occurs when the gravity of a dying massive star is so overwhelming that its matter falls straight inward, instantly replacing the star with a silent black hole. Black holes aren't the only things wandering the dark. There are also rogue planets, entire worlds that formed normally, only to be ejected from their host star systems by gravitational chaos. Unbound by gravity, these planets drift alone. They experience total sensory deprivation, spinning in endless night without the warmth, light, or rhythmic pull of a host star. Alongside the vibrating plasma and pulsing light of the cosmos, there is a silent countermelody. Billions of massive objects have dropped off the cosmic grid entirely, wandering unseen through the space between the stars. The rhythms of light, matter, and stellar heartbeats rely entirely on the physical fabric of space-time they travel through, and there are extreme environments where that fabric stretches to its breaking point. This is the supermassive black hole at the center of the galaxy M87, and that glowing, asymmetrical ring of hot gas marks the event horizon, the absolute boundary of its influence. This animation shows how a deep gravitational well warps the flow of time. According to general relativity, extreme gravity creates gravitational time dilation, a phenomenon where the passage of time slows down in intense gravity compared to weaker areas. Because of this warping, perspective dictates reality. If you stood safely far away and watched an object fall toward that event horizon, you would see its heartbeat slow down infinitely, eventually appearing to freeze in place. The cosmos plays its song in a room that bends, stretches, and dictates the tempo. Gravity acts as the ultimate conductor, shaping a living archive where stars sing their histories across the fabric of time. Look up on a clear night, and the sky presents itself as a peaceful, unchanging canopy. From our vantage point on the ground, the cosmos appears as a quiet roof suspended over the Earth. This vintage astronomical chart illustrates how we often teach the solar system, a flat, orderly clockwork of planets following perfect circles. It's a model built on the idea of predictable, localized stillness. But this perception is a sensory illusion. Because the vacuum of space lacks air to carry sound or an atmosphere to provide friction, our senses interpret the silence as a lack of activity. The cosmos is an active system of unseen forces, a high-speed drift occurring at every scale simultaneously. Even the stars are restless. They are active bodies of plasma, clouds of ionized gas where electrons and nuclei move independently, creating a state of constant, violent internal churn. Deep inside that plasma, intense pressure and gravity create slow, rhythmic ripples known as pressure waves. The study of these internal tremors is called astroseismology. As these waves reach the surface, the entire star physically oscillates, ringing like a bell. We use these vibrations to study our sun, helioseismology. By tracking these pulses, scientists map the solar interior, revealing twisting rivers of hot gas deep below. Every star in the sky is a vibrating instrument. These internal tremors define a star's physical structure, ensuring that even the most massive celestial bodies remain in a state of constant activity. This kinetic energy remains active even at the end of a star's life cycle. A cosmic death is a dynamic transition, though the scale of that motion varies wildly between stars. Massive stars often end in a supernova, an incredibly violent, brilliant explosion that briefly outshines an entire galaxy. This event, like the one that created the Crab Nebula shown here, blasts shockwaves of gas and heavy elements across space for thousands of years. Other stars experience a direct collapse. The star caves inward so suddenly it becomes a black hole without a single spark of light, vanishing from the visible universe in an instant. Smaller stars, like our Sun, fade over billions of years. They shed their outer layers to become white dwarfs, dense Earth-sized cores that quietly radiate away their leftover heat until they eventually dim into darkness. Whether through a blazing shockwave, a sudden collapse, or a billion-year fade, the end of a star is a massive kinetic event. The spaces between these stars are equally active. Even the deepest shadows of the galaxy are crowded with hidden matter. Billions of rogue planets drift through the Milky Way. These are unbound worlds wandering through the dark, without a host star to warm them or a solar system to call home. Surrounding these worlds is dark matter, an invisible form of mass that does not interact with light, but provides the gravitational scaffolding that holds galaxies together. This motion is happening right here. Trillions of dark matter particles flow silently through the Earth and your own body every single second. The empty void is actually a rushing river of unseen particles and wandering rogue worlds. Stillness does not exist, even in the dark. To understand our own movement, we have to look past the static, two-dimensional maps of the solar system. The Sun is currently orbiting the center of the Milky Way at nearly 1 million kilometers per hour. Because the Sun is moving so fast, the planets are dragged along behind it. They follow the Sun in a twisting, helical corkscrew pattern, trailing its path through the galaxy in a continuous spiral. We are participating in a system of orbits within orbits, a graceful, ceaseless drift that carries us through the galaxy every moment of our lives. The stillness we feel on the surface of the Earth is a localized illusion, masking our actual trajectory through the high-speed mechanics of the galaxy. At the largest scales, even the deepest intergalactic voids are in a state of change. These regions sit at 2.7 Kelvin, a temperature just above absolute zero that serves as the thermal echo of the universe's birth. These freezing voids are physically growing. The structure of space between galaxies is constantly stretching and expanding. This expansion is accelerating, pulling distant regions of the cosmos apart faster than the speed of light. Empty space itself is physically growing, pushing distant galaxies beyond our cosmic horizon and out of our reach forever. The universe is an ongoing event we are riding through. From vibrating atoms to stretching voids, the only constant is beautiful, ceaseless drift. To our eyes, the deep vacuum of space appears perfectly empty and silent. But at the subatomic level, space is crowded with quantum fluctuations, the constant random appearance and disappearance of tiny particle-antiparticle pairs. In a fraction of a second after the Big Bang, a process called cosmic inflation caused space to expand faster than the speed of light. This rapid expansion caught those tiny quantum blips and stretched them to cosmic proportions, freezing them into place before they could vanish back into the void. These stretched anomalies became the seeds of the universe, dense pockets of energy where gravity eventually began pulling matter together. The largest structures we observe today, from massive galaxy clusters to the planets beneath our feet, began as the microscopic trembling of absolute nothingness. We see the remains of those quantum seeds in the cosmic microwave background, the oldest light and heat signature in the universe. Inside this heat map lies a massive anomaly known as the cold spot. It spans hundreds of millions of light-years, and its presence doesn't quite match the smooth randomness we'd expect from early universe physics. Some theorists suggest this spot is the imprint of a vast cosmic void, while others wonder if it marks a collision between our universe and a parallel one. While its origin remains a subject of intense debate, this unexplainable void stands as a physical reminder that the macroscopic universe is still shaped by the unpredictable forces of its birth. Within the galaxies formed from those early seeds, matter clustered into stars and planets that often defy our expectations. Contact binary stars orbit so closely that their outer layers touch, creating a constant, spiraling exchange of stellar material between the two suns. Our own solitary sun is a rarity. It may have once shared our system with a twin star named Nemesis that drifted away into the galaxy eons ago. In systems with high carbon levels, intense gravitational pressure can turn the cores of dead stars into diamond planets, worlds made of solid, glowing crystal. Other worlds are completely unbound. These rogue planets are violently ejected from their solar systems by gravitational chaos, left to drift alone through the dark. The order we see in our own solar system is only one path. The universe is a chaotic engine, constantly generating extreme exceptions. This concentrated mass physically alters the environment around it, curving the geometry of space and time. This means the flow of time is not a constant rhythm. Instead, it is deeply linked to the strength of gravity in any given region. General relativity tells us that extreme gravity, like the region surrounding a black hole, slows down the passage of time relative to an observer further away. This is a measurable physical reality. Satellites and atomic clocks on Earth must account for these tiny differences in time to remain accurate. The mass forged from those early quantum fluctuations governs the passage of time, turning an abstract concept into a variable shaped by gravity. Surrounded by time-warping black holes and rogue planets, where does our own world fit into this chaotic map? Mapping the invisible wavelengths around us reveals that our solar system is currently dwindling through the local bubble, a hollowed-out cavity 1,000 light-years wide. This massive void was cleared by the expanding shockwaves of ancient supernovae, which blasted the surrounding gas and dust away from our neighborhood. This violent past created the low-density, quiet chamber we inhabit today, providing the peaceful backdrop required for our solar system to thrive. Our journey tracks from microscopic quantum boiling to anomalous cold spots, diamond worlds, and the carved-out bubbles of our own stellar backyard. Everything we see, from the bizarre extremes of deep space to the quiet home we call Earth, is the macroscopic result of the universe's tiniest quantum tremblings. When you step outside on a clear evening and look up, the sky appears perfectly still. It feels like a quiet, motionless canopy of stars suspended in the dark. Space is filled with extreme, violent energy. The difference is, the most powerful events in the cosmos happen in absolute silence. Right this very second, trillions of these invisible, nearly massless particles called neutrinos are passing right through you. These particles were forged in the cores of exploding stars and the intense heat of the early universe. They travel at nearly the speed of light, and they fly through the entire planet Earth without hitting a single atom or leaving a single trace. To understand the real mechanics of the cosmos, we have to look past the light our eyes can see and trace the invisible forces shaping everything from the smallest particles to the largest structures in existence. When a massive star runs out of fuel, it usually dies in a brilliant supernova, leaving behind expanding shells of glowing debris, like the complex filaments we see here in the Crab Nebula. Other stellar deaths leave a darker footprint. Consider a magnetar, a collapsed city-sized dead star wrapped in a magnetic field trillions of times stronger than Earth's. That invisible magnetic field is so intense, it can distort atomic structures and tear surrounding matter to shreds. All of this extreme violence unfolds without a single sound. Yet even a magnetar leaves a trace. For the absolute heaviest stars, the end is a complete, silent disappearance. In a process called direct collapse, gravity pulls with such sudden, overwhelming force that the entire star simply vanishes inward. No explosion, no flash of light, just an instant plunge into a dense, inescapable black hole. On the stellar scale, the most absolute cosmic endings lack fireworks entirely. They're simply quiet, dark gravitational traps. Zooming out from individual stars, entire galaxies operate under the same quiet rules. They interact, collide, and consume each other in a process known as galactic cannibalism. Larger galaxies exert immense gravitational tidal forces on their smaller companions. Over billions of years, these small satellite systems, like the Magellanic Clouds orbiting our own Milky Way, are slowly stretched, torn apart, and absorbed. The Milky Way is on a slow-motion collision course with the Andromeda Galaxy. While its glowing spiral is still 2.5 million light-years away, the vast invisible halos of hot gas and dark matter surrounding both galaxies are already touching. As these massive structures merge, they leave behind fossil stars on their outer edges. These ancient survivors carry the chemical makeup of a much younger cosmos, acting as silent witnesses to collisions that happened billions of years ago. Galaxies are active battlegrounds, slowly consuming their neighbors through the relentless pull of unseen gravity. This visualization shows the largest mapped scale of reality. Galaxies gather along a vast, hidden scaffolding known as the cosmic web. Pulled along immense dark matter filaments, this structure looks uncannily like a neural network. Dense galaxy clusters mirror neurons, connected by filaments like axons. While gravity gathers matter along these heavy dark matter threads, the empty cosmic voids in between are constantly growing. The silent expansion of space itself is stretching those gaps wider every second. Everything we can see, every star, every glowing cloud of gas, is dictated by this invisible architecture. When you step outside and look up at the night sky, it still looks perfectly still. That sense of total peace is an illusion. You are standing in the crossfire of ghostly neutrinos. Above you, massive stars are vanishing into deep gravity wells, and entire galaxies are being pulled apart across a web of dark matter. The blazing stars and swirling galaxies we map with our telescopes are the decorative foam riding on top of a deep, invisible ocean. The cosmos is a masterpiece of quiet violence and hidden structure. The true power of the universe lies entirely in the forces we will never see and the events we will never hear. Right now, there are thousands of worlds drifting through the spaces between stars. This is a rogue planet, a dark, frozen sphere moving silently through the deep void, completely unbound from any sun. These planets are often refugees, violently ejected from their home systems by the gravitational chaos of other worlds. Some never had a home to begin with, forming on their own like failed stars that were too small to ignite. Astronomers estimate there are billions of these lonely worlds in the Milky Way. They are so common they likely outnumber the stars we see in the night sky, yet they remain nearly invisible in the darkness. On a rogue planet, there is no sunrise and no sunset. Without a star to provide warmth or light, the surface remains in a state of eternal night, where the only thing visible in the sky is the faint, cold glow of distant star systems. When we view the cosmos from this isolated perspective, the universe feels like a disconnected, silent void. It appears as a place where worlds are scattered randomly, drifting completely alone. Zooming out from a single planet to the intergalactic scale reveals a highly structured physical web. At this level, the seemingly empty void is actually a dense network of matter and energy. Most of the mass in this network is dark matter. This substance doesn't reflect or emit light, but its presence is felt through gravity. It acts as a heavy, invisible anchor for everything else in the cosmos. Dark matter forms enormous invisible filaments across billions of light years. This structure, the cosmic web, serves as the universe's scaffolding. Galaxies gather at intersections, leaving vast cosmic voids between. Remarkably, this arrangement looks identical to neural networks inside the human brain. This physical framework holds the entire cosmos together. The universe is a single interconnected system, organized by a web of gravity that spans the darkness. We can see this architecture in action within our own cosmic neighborhood. The Milky Way is part of a small group of galaxies that are all bound together by the same invisible threads. Our closest large neighbor, the Andromeda Galaxy, is currently moving along a dark matter filament that leads directly toward us. In about 4 billion years, our two galaxies will begin to merge. We are already beginning to touch. The vast halos of hot gas and dark matter surrounding both galaxies are already overlapping as we draw closer. This merger is a slow-motion blending of stars and gravitational orbits. Because stars are spaced so far apart, they will simply pass by one another as the two galaxies eventually settle into a single, larger system. These massive galactic islands are part of a continuous movement. They are being guided by a universal architecture that constantly draws matter together. This connection reaches all the way down to a single human element right here on Earth. The elements that make up your body, the carbon in your cells, the calcium in your bones, and the iron in your blood, were not present when the universe began. These atoms were forged millions of years ago inside the intense, burning cores of ancient stars. They are the products of nuclear fusion, created under pressures that only exist in the hearts of the most massive suns. When those stars died in spectacular collapses, they scattered these heavy elements into space. That stardust drifted through the cosmic web for eons before gathering to form our planet and, eventually, you. Your biology is constructed from these physical remnants of the early cosmos. Every atom in your body carries a chemical signature from the death of a distant star. Because your consciousness arises from these same cosmic materials, you are the universe beginning to observe itself. You are a moment where the matter of the cosmos has become aware of the very structure that created it. Recognizing this atomic connection turns the dark expanse of space into something familiar. It is a place of peace and belonging, a vast, quiet stillness